Hello, and welcome to our project. My name is Kerwin Mercado,
And I'm Ethan Hansen.
and our project is about artificial intelligence for augmented reality. Our work is sponsored by General Dynamic Electric Boat. Object detection is a challenge in computer vision. The purpose of this project is to see whether or not CNNs could improve upon current object detection capabilities of General Dynamic Electric Boat. The deep learning approach we use is called RCNN, specifically faster RCNN. RCNN stands for Region Convolutional Neural Networks. RCNN allows us to perform object detection. The architecture of faster RCNN can be complex due to various moving parts. But if we take a look at this diagram, at first we can see an image of a woman and a bike. The woman is in purple towards the right, and the bike is blue towards the left. The representation of our image will be in a multidimensional array consisting of height, width, and depth. The orange figure here is a pre-trained CNN that prepares our data for the Region Proposal Network, also known as the RPN. The gray figure is a convolutional feature map which gets passed into the RPN. The purpose of the RPN is to find predefined numbers of bounding boxes which may contain the object we're looking for and place an anchor on it. What anchors allow us to do, it allows us to frame the object detection problem into one, does this particular anchor contain the relevant object? And two, how can we better fit the anchor onto the relevant object? After having a possible set of contenders, we use a region of interest pooling to extract features of the relevant object onto a new multidimensional array. Finally, we use an RCNN to classify and adjust bounding boxes to get our result.
In order to use the model, we first have to create a data set. The images in the data set must have a similar environment and be small in size. The similar environment is important in order to train the model on what obstacles may be surrounding the object you're trying to detect. Small images is only necessary if you lack time and memory. You can certainly use a lot of large images, just that's going to max out your computer's memory and take a very long time to train. Once you have your images, you're going to want to divide it into two folders, train and test. And despite the naming convention, those are both used during the training process. And those two folders should be equal, or the training folder should be larger. Then for each photo, you want to create a label for the object using the label image program. The label image program allows you to draw a rectangular box around your object and label that box with whatever label you are working with. And then you're going to save that as an XML file, which the example XML file shows that the location of the bounding box is saved right here where it says xmin, ymin, xmax, ymax. And that XML file is going to be used in the CSV conversion. You're going to need to convert all of your XMLs that you just made using the label image program to CSVs. CSVs can be used by the OpenCV library, and we were able to convert our XMLs to CSVs using the XML to CSV.py file found in the Raccoon dataset. And then using those new CSVs, you generate TF records using the generate tfrecords.py file. And what TF records are, is it's going to act as the labeler for your model. As you can see down here, when it generates TF records, it returns a certain integer. And then you're going to create a label map, which maps those integers to your label. And that's how your model is going to be able to identify the object. Then during the training process, it's going to look something like this. We use the faster RCNN Inception V2 PETS model from the Model Zoo GitHub. And then our training statistics using an 82 image data set. At step 1, we had a loss statistic of 1.42. Ideally, you want your loss statistic to be smaller than 1 and even better, smaller than 1/10. And we eventually get there. At step 101, we had a loss statistic of 0.2, which is significantly better than 1.4. And then at step 201, we had a 0.12, which is even better. Step 283, we got 0.05. We finally hit under that 1/10 mark. And then the next step, we actually went back up to 0.069. And then at step 483, we went back down to 0.039, which we saw fit to test the model. We originally tested our model using a 12 image data set with very large images, like 3,042 pixels by 4,032 pixels to be exact. And the issue we got was that the bounding boxes it mapped were off in the y direction. So as you can see in this image, the bounding box does not fully fit the object in the y direction, and thus the y coordinate for the center is a bit off. You can see using the graph here that it says the center is like 2,300. 2,300 would be roughly here-ish, and we're missing a bit there. Same goes for the next photo. We're again off in the y direction. We have a bunch of extra space here at the bottom of the object, and that's going to impact the center calculation. And then in our last image, we had it off in the x direction and the y direction, which really screws up the center. But then we found greater success using a larger image data set, but with smaller images, 800 pixels by 600 pixels. And then in these pictures, you can see that there's minimal error in the x and y directions, and the bounding box is pretty accurate, 97%. And then the following images shows similar results, but with a different environment. As you can see, we were able to achieve incredibly accurate object detection using this faster RCNN model, and that's exactly what Electric Boat wanted us to find out. We have fully shared our findings with them, and they are now implementing it at their company. And that is our work on senior design. Thank you.